Hello, I'm Nicholas Berger, and I'm going to be discussing our Lab 2 for Physics 2211. So in this lab, we dropped an object from a height, and I dropped a tennis ball. As you can see right here, I'll play the video. I propped my camera up on my desk, and I just dropped it. So I think my hands, yeah, there's my hand right there. So I dropped said tennis ball. Unfortunately, I recorded this video vertically, but Tracker said that it was going to be horizontally, and I wasn't sure how to flip it, so the direction is an X, but I just changed that to negative since from this is the origin and it's going into positive X. When I translate this into my combined graph, I just make all these values negative. And also, my camera was tilted, so I just rotated the axis so the fall is along that axis. That did not mess it up because I have like calculate like the magnitude, and I wasn't about to do that, so I just rotated the axis. So the x is what we're paying attention to. The y just is in the same spot pretty much the entire time. So yeah, this is my experimental graph, and then I combined it with my two predicted graphs. As you can see, experimental is this yellow one, no drag is the red one, and drag is the blue one. So I wasn't so the as I was expecting the predicted drag to be the one that traveled the least, as we can see, just because idealized drag and actual drag are two very different things. And the drag coefficient, I looked up for a tennis ball, it's 0.6. I don't know. I have played with this tennis ball. I didn't have any new tennis balls on me, so I'm not sure how that affects it, but I don't think that it would affect it that much, and there could be various or several reasons as to why drag and experimental were so different. It's but no drag that just take that just took into account gravity, so that is why it is in fact the furthest traveling one, followed by experimental, and then idealized drag and gravity. So the models that predict a terminal velocity are going to be drag and experimental. So terminal velocity is when the force of the drag outweighs the force or equalizes with the force of gravity. Since drag is based on coefficient of drag times velocity squared, as in the faster an object goes, the more the drag is going to increase exponentially. So think of it as an aircraft. An aircraft can only reach can reach a certain top speed, and that is because the drag is pushing against the force of the engines. And it is the same idea for a ball being dropped. So when I drop something, it is going to accelerate to a certain point, and then it'll have a net force of zero, as it is not accelerating or decelerating until it hits the ground. So drag and experimental are going to predict that, but no drag will not, because it's the same as there is no as or it's in a vacuumless or it is in a vacuum pretty much, so only gravity is acting on it. So something like an object in space that is accelerating at a constant speed will never reach a terminal velocity. Well, I mean it will when it gets like light, but that's we are concerned with that for this experiment. So let's say the object was initially thrown downward, how that would affect our terminal velocity. I can go to my lab with friction. We don't even have to make a new one, as let's just assume that I threw it at 0.05 seconds and it had a velocity of negative 0.440. It is still, as we still see, it is still going to level out at that terminal velocity. And since we can assume this because this is an applied force, and the momentum principle states that this force will still be here. So a velocity that is below the terminal velocity will not affect it. However, if I were to throw it faster than the terminal velocity, which isn't very fast for a tennis ball because it is rather light, the drag would actually slow it down until it reached that terminal velocity, because terminal velocity is, at the end of the day, a state of equilibrium. Uh, if the ball is going faster than that, the drag is going to heavily outweigh the force of gravity, so it is going to slow it back down. And we can use the same concept for aircraft again. When an aircraft is diving, it is going to go faster than when it is flying straight. But once it levels out straight, the speed it has remains the same. Well, initially it remains the same, so it has a much higher drag pushing on it. So it is eventually going to slow down back to its maximum speed. And it is the same idea for a tennis ball. no matter how hard you hit it, if it does not hit the ground, it will always slow back down to that initial speed. Well, not that initial speed, but it'll always slow back down to a terminal velocity. So that is everything for today, and thank you for watching.